702 and Cape Talk.
The Naked Scientist.
Dr. Chris Smith joining us on the line. It's always a pleasure to talk to you when I can. Chris, good morning.
Hey, Africa. It's good to catch up again.
It is indeed. Let's start off with this interesting story out this week about a blocking of the uptake of fat in the intestine, which could be a game changer, I suppose, in the development of the anti-fat pill.
Yes, researchers in America have come up with a way of stopping the intestine from absorbing the fat in your diet, so that there is the potential to come up with a pill that would mimic this effect, and therefore you could have a naughty lunch and it wouldn't be reflected on your waistline, hips and bum. Now, obviously, it's very early days. This is in mice. But what Anne Eichmann and her colleagues at Yale University have done is they've been studying mice, and they have found that a particular signal, which we have known about for many decades, which is linked to the growth of new blood vessels, also plays a really important role in how a group of tubular structures called lacteals work in the intestine. These lacteals are very thin tubes that pick up fats that we eat and then eventually pass it into the bloodstream. And by blocking these and augmenting these VEGF signals, which affect, normally we thought, the growth just of blood vessels, they can open and close the doors on these lacteals to fat. And so in mice, they manipulated genetically these things, and they were able to show that mice fed the rodent equivalent of junk food for more than a month or two did not gain any weight compared to animals that were fed the same diet and didn't have this modification. And they do have a drug which can mimic this effect. So this suggests that it may be possible in humans in the future for us to swallow a pill which, rather than just block the enzymes that normally digest our dinner, which is one of the existing ways of doing this and has very unpleasant side effects, it might be possible to achieve this and mimic the body's own natural way of opening and closing the door to calories, and therefore limit the absorption. And this means we won't all be looking at having a gastric bypass in a few years' time.
But do we not need fat in our bodies? I mean, why is it there then if it doesn't perform a function? Because we living with obesity, I suppose, because of the diet that we're consuming.
Yes, you raise a very good point, which is that fat-soluble vitamins, things like vitamin A, vitamin D, vitamin E, vitamin K, they move into our body in the fat that we eat and from fat in food. So fatty food tends to contain these things. If you block the uptake of fat, you could be cutting off your supply of those essential nutrients as well. So this is something that needs to be taken into account. But equally important is the fact that now between a third and a half of the entire world population, this is billions of people, are overweight or obese. And obesity is probably the worst health scourge the world faces, because it carries a very high risk of getting diabetes, it carries a very high risk of stroke, high blood pressure, heart attack risk, and it's also really bad for people's joints. And so as a result, we know that giving people just advice on healthy eating and healthy lifestyle isn't working. Profits in McDonald's are up 7.5% already this year. And I'm not saying McDonald's exclusively peddle junk food, but they do serve foods which are associated with people getting fat, as do Burger King and many of the other chains and things. So we know that people's appetite for these sorts of very calorie-dense foods is not going down, it's going up. We know people's waistlines are expanding, so we have to come up with a way that's going to help people to exist in the modern era where there are calories on tap and very tempting treats that are irresistible, but at the same time won't be reflected in their waistline and massively increase their diabetes risk.
Certainly a piece of, research that we'll be following with interest. I will be asking you about TB in a moment or two, but we already have some calls coming in. 2021 446 0567 or 11883 0702. And Chris, your first call is from Linda in Four Ways. Linda, what's your question for Chris? Good morning.
Morning. I want to ask if phobias can be hereditary.
Phobias, can they be hereditary?
Hi, Linda. Well, first of all, what's a phobia? A phobia is an irrational fear of something. And although most people develop a phobia probably because of experience and education, as in I might see a snake and I might react to it and say I'm scared of it, and I might do that in the presence of my children, and my children can learn that from me. And we also know that animals can do this as well. An animal can catch a fear from another animal. Scientists have done experiments on rats, where if you've got one rat which is scared of something, then it will pass on its fear to its offspring, but not because there's a genetic element, it's a behavioural and probably a smell element that transmits that fear. But that said, they the predisposition towards catching a phobia, as in becoming scared of something from a parent or close associates, that could be genetic. And we know that lots of psychiatric, behavioural and mental behaviours are underpinned genetically. And so it may well be that perhaps you inherit from your parents a predilection or a predisposition to develop one of these conditions, but you don't inherit the condition itself.
Okay, can I add another bit to the question?
Go ahead, Linda.
What is the function of phobias, kind of in terms of survival? Some phobias are very, very irrational. Some make sense.
Yeah, in your brain you have a circuit, like a fear circuit, and it involves a structure called the amygdala, which is in your temporal lobe on each side. And these fear circuits are there to protect you. They stop you jumping off of roofs. When you see a big drop on the other side, you don't go tumbling over it thinking this will be fun. You're frightened. So normally these things are kept in check and you are frightened and fearful of appropriate stimuli. But sometimes some stimulus can hijack that circuit and the response becomes extreme, and that's a phobia. And so probably what is happening is that the circuits that are normally there to safeguard your survival, and they work really well. Let's face it, humans have been around for millions of years. There's billions of us, so obviously we're very good at self-preservation. So these circuits are there for a reason. They make sure that we don't take unnecessary risks and we can anticipate risk and we behave accordingly. But if you have a circuit like that, and sometimes it goes into overdrive, or some people have a predisposition for it to overreact, perhaps then, as a result, this protective system can become deleterious, and some people end up with symptoms as a result, and they become over fearful of certain innocuous stimuli.
Linda, thank you very much for that. And I will confess, Chris, I'm one of those people who has a phobia for snakes for absolutely no reason whatsoever. Richard is in retreat. Hello, Richard.
Good day, gentlemen. I would like to know, does human hair continue to grow after death?
Do human hairs continue to grow after death? The answer is probably, but to a tiny degree. Hairs are made by hair follicles. Hair follicles are structures or little aggregations of stem cells in the skin, which are arranged in a ring, which deposit the hair filament, which is proteins, and push it out through the skin. They're therefore dependent on energy from the body's processes to drive the chemistry that makes the hair grow. When you die, the energy supply in the body dries up, and therefore any hair growth is going to be very, very short-lived. That said, if you ask people who work in mortuaries or people who, for instance, are undertakers and care for people when they've died, they will say sometimes they have to give their bodies a shave, or sometimes they do actually notice that the beard on a man appears to be a little bit longer. On the one hand, you could say, well, is that the hair growing? But actually what we think is more likely to be the case is that because the person's tissues all sag, shrink and dry a little bit with death, this makes the hair, which is stiff, rigid and sticking through the skin, stick out a bit further, so it looks like the hair has grown, but in fact it hasn't. It's just that the person has shrunk a bit behind the hair, so it makes it look longer.
So the Hollywood directors and producers have lied to us, because many a scene in a movie has resulted in somebody who'd been dead for a while having this overgrown hair everywhere when their bodies have been exhumed.
It wouldn't be the first time that Hollywood has sold us a fib, would it?
It certainly would not.
702 and Cape Talk.
The Naked Scientist.
We have a number of calls waiting for you, Chris. Let's start in Glen Vista and say hello to John. Hello, John.
Hello, good morning. Chris, when we read about the percentage of genetics of, say, that's shared by chimpanzees and modern human beings, it's about between 98 and 99%. But recently I've been reading about percentages of up to 2 to 5% of Neanderthal genes in Homo sapiens from Europe, and Denisovan genes similarly from Asian Homo sapiens. Somehow that mathematics doesn't work for me. Can you reconcile that? Because 98% versus 100 minus 5, it comes to 95%. So they must be looking at the statistics a different way.
The language is confusing, isn't it? But let me try and clear this up for you. Sometimes you'll see reports where people say that we share a certain number of genes with something, and in other reports they'll say the DNA sequence is 99% identical. These are not the same thing. Now, a gene is just a block of DNA that does a certain job. The gene code, or the DNA that's in that gene, might be different. It might be a gene that does the same job, but it might have subtle differences. So if I just compare how many genes I have that a banana also has, this bananas are always used as the common comparison for some reason, it's about 50 or 60% of the genes that are running a banana, I would find an equivalent gene in me. That doesn't mean if I sequence my DNA, I'm going to see identical DNA sequences in the banana. I'm going to see genes doing the same job with broadly similar genetic code running those genes, but they're going to be adapted to being in a plant. So when we're comparing between species, we might say, well, look, the genes which are in a chimp and the genes in a human are really closely similar. And some of the gene sequences are going to be really, really, really similar. But when we're comparing between a human and a very close relative of a human, like a Neanderthal, for example, there we line up the chromosomes side by side because they are so similar that actually you see almost identical configurations of all the genes, and you compare within each of the genes the actual letter by letter comparison, and there you will see a very, very close match, except it'll be a few percent away, in the same way that, my genes are going to be a bit different to my own children because of mutation and random changes. So I hope that clears it up for you. You've got to be careful you're comparing apples with apples, and the genetic language can be complicated when you're making that comparison. The difference between how many genes you share as just genetic blocks and the actual physical DNA letters that are in those genes. They're quite different entities, and often they get used interchangeably and mixed up rather confusingly when these things are reported, and that perhaps is what you're seeing.
And John, that was a very clever question. Thank you very much for asking it. Bruce is in Claremont. What's your question for Chris?
Hi, Chris. The question I want to ask is about human memory. Some people have phenomenal memories. I mean, I went some years ago and listened to someone. He recited the whole of one of the Gospels in the New Testament, the entire thing without a fault. I mean, it was a kind of 2-hour sort of that he went on. Then the other day I was watching on the TV, and there was somebody was playing Beethoven, one of Beethoven's piano concertos, and the soloist had no music at all, and he played the thing impeccably. How do these guys do this? It can't just be training, because if I trained for the next 50 years, I wouldn't be able to do it. But
Me neither.
Why can some people do it and others can't?
Well, partly it is training. These people have practiced. They weren't born knowing the New Testament, and they had to learn Beethoven. And the way they did that was by relentless practice. And it doesn't just mean you practice reciting it, you actually practice learning it, and you learn how to learn. And there's a number of different ways that people do this. One of them is that there's a lot of talent involved, and some people do have better memories than others. The other thing is that people have learned how to learn very well, and they've learned to use lots of cues and ways of linking information so that they can do that. So in the case of the Beethoven thing, you think, well, how does that guy remember, or the lady remember, all those notes? And actually what you're not considering is that there's more to just playing music than reciting a sequence of notes. It's all the movements that go with it. So you're not just using a physical memory of the music, you're also using how you're going to play the music, what movements you're going to make in order to recall the note sequences. Now, I can give you a simple example of how this works. And I've used this on my students before, and I use it as a reason why when I'm teaching, people should always pick up a pen and make notes in lectures. Because you will encode the information not just as physical facts in your mind, but you will encode the information as the motor movements that you write them down with, and that will help you to recall the information. Now, if I gave you a blank piece of paper and said, I want you, without any cheating, to write out all the letters on a computer keyboard where they are, you would just look at me and say, I have no idea. Unless you make computer keyboards for a living, because there's always some smart aleck who says that. But if, on the other hand, you then thought for a minute, what you might start doing is some ghost typing in front of yourself. And you'd think, well, if I type my name, that would give me where the M and then that E is there and the Y is over there. And very quickly, you'd begin to piece together where the computer keyboard layout is by making motor movements. And very quickly, you'd realise you do know where all the keys are, even though you didn't think you did. And you've stored it as a motor program, movements with your hands. This is exactly what the musician is doing, to remember the notes of Beethoven and play them. It's the emotion wired into the movement, wired into some memory, wired into some talent and a lot of practice. And the person doing the New Testament is almost certainly using similar cues to help them to chunk the information into tractable blocks that they then know how to recall. And that's the trick of being good at memory, is knowing how your brain works, learning how it works, and then learning to learn and then practice.
Another good question, Bruce. Thank you very much. Treasure is in Katlehong. Treasure, what's your question for Chris?
Yeah, morning, guys. Hello?
Good morning. Good morning, Treasure. Go ahead. What's your question?
My question is, I've been to Durban for quite several times now, and I've been asking myself, why is the water tasting salty in the sea? That's my question.
Hey, why is the sea salty?
I've been wondering about that question for the last 40 years. Why is the water in the ocean so salty?
Right, the reason for that is that if you think about where does the water in the river come from, it comes from rain. So let's start with a rain cloud. Some rainwater drops out of the sky, lands on the land, and as it filters through the soil, it picks up tiny amounts of salt and other trace materials, and it washes it into rivers. The concentration is really low, so the water in the river, the water in a lake, and the water running down that river, it tastes fresh. But where do rivers go? Well, all rivers run to the sea eventually, so that tiny amount of salt that's come out of the land that week is now in the ocean. The water then leaves the ocean because the sun shines on it, and the sun illuminates the ocean surface, delivering energy at the rate of about 1 kilowatt per square metre. This gives energy to water molecules and enables them to break bonds with other water molecules, so some water evaporates from the sea. But the salty and mineral particles, they can't leave the ocean. They're bonded far too tightly to the other particles in the ocean. So the only water that gets evaporated from the ocean is fresh water, which goes up and makes a cloud, which then goes over land and starts the whole process off again. That's the water cycle. But so you can quickly see that there's a net movement of salts off the land through erosion and dissolving towards the ocean. So the ocean progressively gets saltier and saltier up to a point, but it doesn't keep getting saltier forever, because once you get to a certain concentration of salts, you then start other chemical processes kicking in, which begin to remove, deposit and form minerals from those salts, which keeps the ocean level of saltiness at roughly the level it's at now, which it has been for millions of years.
Let's go to Chris in Montana. Chris, what's your question for Chris?
Hello. I was listening to one of the programs previously where you said that when people land on Mars, you can actually reverse the process of whatever molecules there are and generate oxygen. Can we not do that here on Earth and use the same machinery to reverse the carbon dioxide buildup and turn it into oxygen?
Wow, that's an interesting question.
Yeah, I think the context of that was we were talking about if we do send people to Mars, how are they going to survive? They're going to need water, they're going to need oxygen in air to breathe and so on. And one suggestion is that we build small nuclear reactors on the surface of Mars to provide us with electricity. That electricity can be used to melt ice, because we know there's lots of ice in the subsurface of Mars, and that will yield water, which we can drink, but then we can also pass the electricity through the water. This will split the water molecules apart in the process of electrolysis. We'll get hydrogen and oxygen. We can breathe the oxygen. We can also use the hydrogen for other stuff. We certainly can do that here on Earth. The idea, of course, was born here on Earth where we are. But the problem is that the amount of energy that you need in order to recover carbon dioxide from the atmosphere and lock it away in a concentrated position, because at the moment it's currently locked away in fossil fuels. The carbon has been packed away into coal and oil and gas, and it's inert and it's locked away in the ground. It's not active in the atmosphere. When we burn the fossil fuel and we release the carbon into the atmosphere as carbon dioxide, you have added oxygen to the carbon. Carbon dioxide is much more stable as a molecule than just the carbon source it came from, and it's very spread out in the atmosphere. And that change, going from a compact, high potential energy state to a low potential energy, very spread out state, we have got the energy out of that process and used it to drive our cars, heat our homes, fly on our aeroplanes. To reverse that process and pack the carbon away again, you've got to give that energy back. And if you do that, the process you do it with is never going to be as efficient as the process of releasing the energy in the first place. So there is a cost. So it'll cost more energy to put the carbon back in the box than getting out of the box. And as a result, where are you going to get the energy from to do that? And you've got to do that in a way that does it in a way that doesn't actually damage the planet. So that's why people are saying the best thing to do with global warming and climate change and carbon release is not to let the genie out of the bottle in the first place, because putting it back in the bottle is a real headache.
And that is it. That's all the time we have this week. Chris, thank you very much for joining us as always. Have a wonderful weekend, and we'll hold over the TB question for Eusebius when he's back next week Friday.
Yeah, thanks, Africa. Thanks, everyone. Have a great weekend. See you next time.